Welcome DKP Sogong aboard. Your learning journey starts now. Ever stared at two numbers and wondered why they're the same? That's the Birch Swinnerton Dyer conjecture for you. An algebraic rank, a count of independent points on an elliptic curve, equals an analytic vanishing order, how fast its L function hits 0 at s equals 1. It's like finding out your shadow and your reflection are secretly the same person. But why? Forget wild coincidences. We're diving into a semantic deep dive. So what's the secret sauce? We introduce the semantic object, calligraphic E. Think of it as the ultimate blueprint, the source code for our elliptic curve. It has finite rules, sure, but crucially, it contains our independent global generative channels. These are the real stars. When we project this onto the arithmetic side, counting rational points, those R channels become the rank. Projected onto the spectral side, looking at the L function's behavior, those same R channels show up as the central vanishing order. It's not magic, it's just one object viewed from two different angles. Now, how do we prove these two views must match? Enter the co-source projection, non-creation, non-erasure theorem. Sounds fancy, right? It basically says, if you have a faithful projection, you can't just make up new independent things out of thin air, nor can you erase existing ones that matter. Think of it like a perfect mirror. It reflects reality accurately, no additions, no omissions. So, since both the arithmetic view and the spectral view are faithful projections of the same underlying semantic object, they must count the exact same number of those precious global generative channels. Boom! Rank E over Q equals 1 of E, S. Simple, elegant semantic. Okay, so the ranks match. But what about the next piece of info after that central zero? The first non-zero term in the Taylor expansion? That's where the refined BSD formula comes in. It's like taking the main equality and zooming in on the details. This formula tells us the scale omega E, the volume reg E of those free channels, and crucially, the size absolute value of SHA-E of the Tate-Shafarevich group. Think of SHA as hidden defects that close locally but not globally. And guess what? Within this semantic framework, the finiteness of SHA pops right out. It's all about conserving the residual closure measure. So, what's the big takeaway? This approach transforms the Birch-Swinnerton-Dyer conjecture from a mysterious numerical coincidence into a beautiful story of one underlying generative freedom seen through two different lenses. It's not about brute force calculation anymore. It's about understanding the structure, the semantics. Math isn't just symbols, it's about the stories they tell.